I am going to discuss about the fact magnetic field due to a long straight conductor. So let us first see the diagram. This is figure 1 and here it is x axis, it is z axis and it is origin O. An infinitely long current carrying conductor which is carrying a current I is placed along z axis, and here I dz is a current element and the distance between current element and the origin is z. Here the point is P and R is the distance between the current carrying conductor and the point where magnetic field to be calculated. And here this angle is theta and this is d theta, very small angle due to the current element at point P. And this point is M and this point is N. So the length between these 2 points M and N is denoted by Mn, and NO equal to Z and OP equal to R, and this is 90 degree perpendicular distance it is between current and the point where magnetic field to be calculated. So this is diagram, and the direction here if we see of magnetic field is perpendicular into the paper, so use this sign, and in previous video I discussed about the sign. So let us see. Let us consider an infinitely long straight conductor carrying a current I. As shown in figure 1. Let us consider an infinitely long straight current carrying conductor as shown in figure 1. Here we consider a current carrying conductor on the z axis which is infinitely long and carrying a current I. We want to calculate magnetic induction field at a point P at a distance r from the conductor lies along z axis. So let us consider an infinitely long straight conductor carrying a current I as shown in figure 1. We consider a current carrying conductor infinitely long and which is carrying a current I and which is placed along z axis. We consider it first. Next line, we want to calculate magnetic induction field at a point P. We want to calculate magnetic induction field at a point at a distance r from the current carrying conductor lies along z axis, which is lies along z axis. Next, from Biot-Savart law, magnetic field at P, the magnetic field at P due to a current element IdZ at a distance Z from the origin O is, so we are going to write from Biot-Savart law the magnetic field due to the current element. We are going to write the magnetic field due to a current element IdZ at a point P, which is given by Biot-Savart law, and in previous video we discussed about Biot-Savart law. And the magnetic field due to this current element at point P we can write from Biot-Savart law, which is dB magnetic field equal to mu 0 by 4 pi times IdZ, that is current element, sin m n p by np square. This is equation number 1. In Biot-Savart law, we discussed that the form of Biot-Savart law is dB equal to mu 0 by 4 pi ideal sin theta by r square, where mu 0 is magnetic permeability, we have already discussed about it, and ideal is current element. In first video on magnetostatics I discussed about current element, and r is the position vector of a point where the magnetic field is given by dB, and theta is the angle between the current element I ideal and the position vector r. This is Biot-Savart law, we already discussed in previous video. Here just comparing with this equation, we can write magnetic field at point P due to current element IdZ in place of ideal. In this form of Biot-Savart law, we write IdZ, this is current element here in this problem, and in place of theta, which is the angle between current element and the position vector, and that angle is theta, and here the angle between the current element and the position vector, that means np here not r is the distance between the conductor and the point. This is perpendicular distance, and the position of this point due to current element is np, is given by np. So the angle between current element and the position vector np is this, and this angle is mnp. This angle is mnp. So in place of theta we can write mnp, and the position, that means r square, in place of r. Comparing with this equation, we can write np, that square, np square. So let us see, from triangle ONP, from the triangle ONP we can write perpendicular z by base r equal to tan theta. This is 90 degree angle. So this is right angle triangle NOP or ONP. This is right angle triangle, and this is perpendicular, and this is base, and we can write z by r equal to tan theta from this triangle NOP or ONP. You can say. So from triangle ONP we can write z by r equal to tan theta, or z equal to r tan theta. Therefore we can write dz equal to r sec square theta d theta. And we can also write np equal to r sec theta, and angle MNP equal to 90 degree plus theta. This MNP, this angle equal to, we can write angle MNP equal to, we can write this angle plus this angle. From geometry we can write it 90 degree plus theta, because of in geometry, if we draw a triangle, and if this angle is theta 1, and if this angle is theta 2, and if this angle is phi must be equal to theta 1 plus theta 2. From geometry we can say it. So we can say here angle MNP equal to 90 degree plus theta. And in next step we use this value dz, np and this angle in this equation. So let us put dB equal to mu 0 by 4 pi I times, in place of dz we write r sec square theta d theta, and sine 90 degree plus theta, that means cos theta. dB equal to mu 0 by 4 pi I, in place of dz we write r sec square theta d theta, and sine MNP, angle MNP equal to 90 degree plus theta, and sine 90 degree plus theta, that means cos theta, by NP square, that means NP equal to r sec theta whole square. In next step we simplify it, mu 0 by 4 pi I times r sec square theta d theta, and sine 90 degree plus theta equal to cos theta, and here r square sec square theta, and we get mu 0 by 4 pi I by r cos theta d theta, because of sec square theta and sec square theta is cancel out, r and r here is cancel out, and r I by r is remaining part, and so dB equal to this. This dB is magnetic field at point P due to the current element IdZ. It is a very small part of the infinitely long straight conductor. So if we want to calculate magnetic field at point P due to infinitely long straight conductor, then we have to integrate this equation, integrate dB, and we will get the total magnetic field. So for an infinitely long conductor, infinitely long conductor, theta varies from minus pi by 2 to plus pi by 2. Why? Let us see this diagram. Let us see this diagram. Here the point P and such. If the conductor is infinitely long, then if this line increases, then the angle will increases. And if the line is so long, infinitely long, then the angle is maximum pi by 2. And if we increase downward direction, if we increase the line downward direction, the angle this will increase. For so long length of the conductor, this angle will be pi by 2, and this is due to the movement of this line, is angle will be minus pi by 2. Thus total magnetic field at point P due to the entire current is B equal to integration of dB, that means integration of mu 0 by 4 pi I by r cos theta d theta, and the limit of integration is minus pi by 2 to plus pi by 2, and this is constant term, so we can write mu 0 by 4 pi, this is a constant term, and I by r also a constant, so minus pi by 2 to pi by 2 cos theta d theta, and we get, if we B0 equal to mu 0 by 4 pi times 2y by r. So this is expression of magnetic field due to infinitely long straight conductor, and we can also write B equal to mu 0 I by 2 pi r. This is another form of magnetic field due to infinitely long straight conductor. In vector notation, we can write magnetic field vector equal to mu 0 by 4 pi 2 I by r phi cap, where phi is a unit vector along the direction in which a right-handed screw advances when it is turned from the direction of current and r. Thank you.